Hello everyone, I want to talk about a little bit regarding the types of chemical reactions and go over some examples so that this will be of a bit more clarification for all of you and refer to your ability to complete the questions. First of all, there are several types of chemical reactions. We will cover the basic types of chemical reactions here. Let's start with the types that we're going to cover. First of all, we have the types that are listed as a reaction that would be part of a double replacement reaction. So let's make that double replacement. A double replacement is exactly what it sounds like. In other words, it is going to involve a reaction in which two materials that are ionic, typically dissolved in water, forming separate ions. And these ions, when the two solutions of water are mixed together, will react to form two new compounds. So let's take an example that I think you're all familiar with and walk through the details. If we take an example of materials such as silver nitrate, and if we dissolve the silver nitrate in water, we have an aqueous solution. If we add water to the silver nitrate, what we really end up with is silver ions and nitrate ions dissolved in water. So what we would have would be silver with a +1 ion, say Q, plus nitrate ions dissolved in water with a -1, let's say Q. Now if we take a second solution and we add to it sodium chloride and dissolve that in water, what we have again in the second solution is sodium ions, +1 AQ, plus chloride ions, -1 AQ, freely moving around in that second solution. Now, when these two solutions are mixed together, a reaction occurs, and the reaction results in the formation of a product that precipitates, forms a solid. In this case, it is silver chloride as a solid, plus an aqueous solution of sodium nitrate, AQ. So this looks like silver chloride, of course, is not separating into ions because it's not soluble in water, and it is more tightly held together by the matrix of the silver ions, and the chloride ions and the water molecules interact with it only very poorly and so can't separate it. On the other hand, the sodium nitrate is very soluble in water, so we actually end up with sodium ions in solution plus nitrate ions in solution, and these are, of course, available to move around, whereas the silver chloride is actually a solid and tends to form a cloudy suspension at first, which eventually coalesces into solid particles of silver chloride, which tend to fall to the bottom. Okay, now this reaction is an example of a double replacement reaction. In order for you to be able to work with double replacement reactions, one of the things that you have to do is to know the details regarding the process of precipitation, for example, and you have to know what types of compounds are soluble and what types of compounds are insoluble. And those are expressed very in the chapter 7, which also lists solubility rules. And the solubility rules are examples in section 7.5. Okay, now once we've written this reaction and we have balanced it, obviously, in this one, the balance is simply the number coefficient of 1 across all the items. We can then break this up into individual total ionic reactions. So this one would be called the molecular reaction. So this one is the molecular form. This one is the total ionic form because it shows all the ions. And now you can see that there's some issues here that you can very quickly evaluate to show that, hey, in this case, we have some ions that have not reacted. They're the same on both sides. For example, the nitrate ion did not undergo any changes. Sodium ion did not undergo any changes. So consequently, those are known as spectator ions. Well, this is a spectator ion. Okay. Now, what did react, and we can then see that if we remove the spectator ions, we have a material reaction in which we have, for example, silver ions from any source is what it means here, plus chloride ions from any source, if we had them, would, if we mix these two things together, immediately interact to form silver chloride, which would precipitate in the solution, and we would have a salt. Let's see, that's an example of the net ionic reaction. And so here we could write a double replacement reaction in which a process yields a precipitate. This is very common and why it's necessary for an understanding of what is soluble and what is insoluble. Let's take a look at another type of double replacement reaction and go through the similar process. Suppose that we had some sodium hydroxide, all right, sodium hydroxide, right, and we allow this to dissolve in water, so it's aqueous, and we're going to add to it an aqueous solution of hydrochloric acid. And we want to know what's going to form in this reaction. Well, this is a case of a special type of subset of double replacement in which what we commonly refer to as a neutralization reaction, because here we have a base. And so if we rewrite it, we'll say sodium hydroxide, which of course is soluble, also a component of most of it is lye, it's a component of most drain cleaners, and hydrochloric acid, which is HCl, AQ, which is the acid in production in our stomach. If these two interact and mix, then what we will form, again, the positive ion from one side interacts with the negative ion on the other side and vice versa. What we're going to form in this case is sodium chloride, and if you look at the table, you'll see that that is completely soluble, solubility rules. And we also have this other interaction between the hydrogen ions and the hydroxide ions, and that forms HOH, which is, of course, water, which is a molecular compound, not an ionic compound. So now if we break this apart into ions, we can see that what we're going to have is, in this case, sodium ions in solution plus hydroxide ions in solution. If we add them to a solution of hydrogen ions, and chloride ions, we're going to end up with a solution still of sodium ions plus chloride ions plus the molecular compound water, which is not ionic. And again, if we write the net ionic reaction here, we're going to be examining this overall reaction, in which we have hydroxide ions from any source. If they encounter hydrogen ions from any other source are going to immediately react to produce HOH as a compound. And this is the example of a neutralization reaction in which you have the production of a salt and water when an acid reacts with a base. Okay. Now, let's take a look at another example here. So, well, before we go too far, point out that this is the total reaction. Total reaction. This is the total ionic reaction. I guess this one should be called actually the molecular reaction. This is the way most books refer to it. And then, of course, we have total ionic reaction, and then we have the net ionic reaction. Okay. Now, what I want to make clear is by using one more example of double replacement. In this example, we're going to take, again, something like sodium chloride in an aqueous solution. And this time we're going to add to it potassium nitrate in an aqueous solution. And again, effectively, the ions change partners. So we would end up with, for example, sodium nitrate in an aqueous solution plus potassium chloride in an aqueous solution. Now, if you examine the solubilities of each of these, this, of course, is sodium ions plus chloride ions when dissolved in water, and then added to that would be potassium ions plus nitrate ions to yield sodium ions plus nitrate ions plus potassium ions plus chloride ions. And in this case, you notice that all the ions are completely soluble. So if we were to mix these two materials together in an aqueous solution, we would have no net reaction. And that is because everything is actually soluble. Now, if you took another step here and you said, oh, okay, all of this is in water, what happens if we evaporate the water? What will we find? What we'll find is a mixture of all four of these things. Because as soon as you evaporate the water, you're going to end up with some sodium chloride, you're going to end up with some potassium nitrate, you're going to end up with some sodium nitrate and some potassium chloride. So there has been no net reaction here because all of the ions are soluble. Okay. Now, that set is a collection of double replacement type reactions. In one case, you form a precipitate, another case, you form a molecular compound, and in both cases, the formation of either the precipitate or the molecular compound results in a net ionic reaction. The next type of reaction that I'd like to discuss with you is that of a single replacement reaction. And a single replacement reaction is exactly what it sounds like. One item is replaced in an ionic reaction with another ion. And what we're going to typically look at, for instance, is metals reacting from a form in which they have no charge, for instance, to something in which they acquire a charge. Now, there's all manner of variation on this. This also can be done with non-metals too. So let's take an example. Suppose we had some zinc metal, solid strip of zinc metal, and we were to put it into a solution of sulfuric acid. What will happen is we will end up with a material known as zinc sulfate, and just soluble, and hydrogen gas, which is a molecular covalent compound. So over here, effectively what we have is a replacement. Zinc replaced the hydrogen in this process to yield zinc sulfate and hydrogen gas. Now, if we open this up into a form to discuss the ionic components, any element as the element does not have a charge, so this would have a zero charge. In the context of sulfuric acid here, we could write that we have two hydrogens, and this is a bit of an oversimplification, but it's okay. An aqueous solution plus sulfate ions, an aqueous solution, to yield zinc sulfate. So we have zinc plus 2 ions here, aqueous solution plus sulfate ions, an aqueous solution, plus hydrogen as a gas, which does not have a charge. So again, if we look at this and examine what ions are the same on both sides, we notice, of course, that it's the sulfate ions. And in this case, what we can say is the sulfate effectively is a spectator ion here. So what this says is when zinc metal encounters hydrogen ions from any source, the zinc metal donates a pair of electrons, and the hydrogen plus 1 accepts a pair of electrons, 2 of them, one for each hydrogen ion, and the zinc forms a zinc ion, the plus 2 charge, and the 2 hydrogen ions with the 2 electrons combine to form hydrogen gas, which actually leaves the reaction mixture. So here we have a single replacement reaction of a metal replacing the hydrogen. So what we also say in this scenario, in addition to this single replacement, we also say that in this context, we say that zinc metal is of greater activity, or let me rephrase that, zinc metal is more active than hydrogen, because it can replace the hydrogen in an acid. Let's take another example. And I want to emphasize a couple of things here in a minute. Let's just take one more example. Suppose that we had some magnesium metal as a solid. Of course, it has no charge. And we added it to a solution of copper 2 chloride, which is an aqueous solution. It's soluble. And what we would end up with here in this reaction is magnesium chloride in aqueous solution plus copper as a solid. Now, again, let's break this up. So we have magnesium as a solid plus what we're going to add to it from a solution of copper 2 ions plus 2 chloride ions. And what we're going to end up with is magnesium plus 2 ions plus 2 chloride ions plus copper coming out as a solid. And again, if we write the net ionic reaction, what we have is the chloride ions, of course, are spectator ions over here. So we have magnesium metal reacts with any source of copper 2 ions to form magnesium ions plus elemental solid copper. So you can see that what we have in this case, just in the previous case, is we have a single replacement. Again, we would say that magnesium is more active than copper, meaning that if we have a soluble solution of copper and we put it in water and allow magnesium metal to be placed into that solution, magnesium metal will interact with this and form the soluble magnesium salt, and copper metal will be released into a precipitate form.
In all of these single replacement reactions, there's one more consideration to talk about, and that is the electrons that are moving here. And in this case, in all single replacement reactions, there are electrons that are given up by one material and picked up by another material. So when we lose electrons, we call that an oxidation. When we gain electrons, we call that a reduction. So this is called a redox reaction, as a reduction oxidation. So every time something loses electrons, something else gains electrons. So let's take a look at this last example to be more specific in terms of what is going on. In this case, you notice that the magnesium is a solid element of magnesium, has no charge on it. It has an equal number of electrons to all of the protons. However, when it finishes this reaction, the magnesium now has a +2 charge, and it's in solution. Well, if it has a +2 charge, that means it gave up 2 negative charges. There's anything that's moving here from one place to another on the electrons. So if it gains a +2 charge, that means it really gave up 2 negative charges, which can be represented by the 2e symbol here, -1, those 2 electrons were given up. Now those 2 electrons have to go someplace. And what we're going to see, obviously, is that they have to be picked up by something else. So this step right here is called the oxidation step, or the oxidation half reaction, because it's half of the reaction. Now every time you have an oxidation, you have a reduction. But first, let's make sure we understand what happened there is the magnesium was oxidized. So magnesium metal is oxidized to form magnesium ions. Okay. So if the magnesium metal is oxidized, then of course something was reduced. That something, of course, is the copper, and it's copper ions. So here we have copper plus 2 ions in solution, and that's how they start off. What they end up is copper metal. So copper plus 2, which means it's copper which is missing, which has 2 more protons than an electron, means it's missing 2 electrons. If we add 2 electrons to this, then the charge becomes 0, so we end up with copper 0 as a solid, and this is the reduction half of the reaction. This is also the reduction half reaction, it's called. Okay, so now we have an oxidation and a reduction. And of course, if we combine these, we can see that we have a situation where magnesium 0 goes to form magnesium plus 2 electrons, and we have copper plus 2, this is a Q, this is a Q plus 2 electrons, forms copper 0, and of course the electrons being on both sides of the reaction means that they cancel out, so of course we end up with magnesium metal plus copper ions, result in the formation of magnesium ions plus copper metal. So the reaction is often expressed as magnesium has reduced the copper 2 to copper 0. Write that out. Magnesium reduced the copper plus 2 to copper 0. So we call magnesium the reducing agent because it's carrying out the reduction, and we call the copper plus 2 the oxidizing agent, because it's accepting the electrons. And so we have an oxidation reduction, or reduction oxidation, known as a redox reaction.
Alright, now, in addition to single replacement reactions, double replacement reactions, we also have what's known as combination or synthesis reactions. So these are combination sometimes called synthesis reactions. And this is where we take simpler materials such as elements, etc., and make one more complex reaction. An example here might be taking the material zinc, for example, as a solid, and allowing it to react with oxygen. It's a gas. Now this can happen relatively quickly if the zinc is made into tiny particles and the oxygen is at high concentration. But what we end up with is zinc oxide, solid. You may recognize zinc oxide as one of those materials that's found as a white, thick, pasty material that is sometimes used to prevent sunburn. zinc oxide paste and zinc oxide cream. Now, in this case, of course, what we're looking at is a reaction between the metal, zinc, and in its elemental form, and oxygen as the diatomic oxygen in its elemental form. Now, in the formation here, we've written out the reaction to represent the initial reactants on the left and a product on the right. It's obviously not balanced. So we have zinc reacting with effectively 2 atoms of oxygen inside an oxygen molecule to produce a material, zinc oxide, which is actually a somewhat ionic compound as a solid. So this has to be balanced. So balance here is pretty straightforward. It really says that we have 2 molecules or 2 moles of zinc have to react with 1 mole of oxygen, molecular oxygen, to form 2 moles of zinc oxide. Okay, so this combination reaction can also be evaluated a bit more in terms of what is going on with the electrons. So in this case, we learned earlier that the zinc as a solid, its elemental form, has a 0 charge. By the way, these charges that we're putting on the structures represent what is known as oxidation numbers. They're called oxidation numbers. Okay. Every element in its natural elemental state has an oxidation number of 0. So here, the oxygen, again, is in its elemental state, so it has a charge of 0 also. But once they react, what you see is that the zinc, we have 2 zinc, and each zinc is a +2. And each oxygen is now a -2. So let's take this apart a little further and say, well, here, what we're seeing is the zinc is starting off at a 0 oxidation state, and the zinc is ending up in a +2 oxidation state. So clearly the zinc lost some electrons. Okay? So in this case, it lost 2 electrons. But if we have 2 zinc moles, and then we have 2 zinc ions, we would have lost 4 electrons. Now the oxygen, or each oxygen atom inside a molecule of oxygen gas, has a 0 charge. But now what we have is 2 sets of oxygen ions attached to a zinc to form the zinc oxide. So in order for the 2 negative sets here, so we have 2 times -2, there's a total of -4 on this side. That means we have to have 4 electrons that are picked up on this side. So in this case, again, you see that if we add up the 2 materials, we see that the zinc has, if you will, lost 2 electrons, and the oxygen has 4 electrons because there's 2 zincs, and the oxygen has gained 4 electrons. It's 2 oxygen atoms each molecule, each gaining 2. So over here we have the reducing reaction, and here we have the oxidizing reaction. So I'm sorry, I did this. Make sure there's an error there. The zinc gave up the electrons, so it is the reducing agent. And the oxygen picked up the electrons, so it is the oxidizing agent, hence the name. Now, the reducing agent is always oxidized. In other words, it loses electrons. And the oxidizing agent is reduced. In other words, it gains electrons. So here we have a combination reaction and a transfer of electrons. So let's go through another example, similar situation. If we had some magnesium metal, 0, plus some sulfur, it's a solid, 0, and we put them together and mixed them up very well, and started the reaction by adding a little bit of heat to start off, we would end up with magnesium sulfide. And this would be as a solid. Again, we have a similar situation. So over here we have magnesium in a 0 oxidation state. And over here we have magnesium in a +2 oxidation state. Well, if the magnesium is in a +2, it had to have given up 2 electrons. And over here we have sulfur in an oxidation state of 0. And over here we have sulfur as the sulfide ion with an oxidation state of -2. So if it became a -2, that means it had to gain 2 electrons. So here we have the reducing agent, which is the magnesium. Here we have the oxidizing agent, which is the which is in this case the sulfur. So the sulfur gained 2 electrons to become sulfide. So what we say is this is a reduction reaction. And the magnesium lost 2 electrons, so this is the oxidation reaction, F. So hence we have a redox reaction again. We say that the magnesium metal was oxidized to magnesium ions, and the sulfur element was reduced to sulfur ions, to sulfide ions. Now, in all of these oxidation reduction reactions, or redox reactions, it's possible to run the reaction in the other direction if we add enough energy. So in this case, for example, if we had magnesium sulfide as a solid, and we put it in a vacuum to prevent air from entering the reaction, and we heat it very strongly, we can recover magnesium as a solid plus sulfur as a solid. This would be called a decomposition reaction. And of course, we could run every one of the other single replacement reactions or combination reactions in reverse if we add enough energy to the system. So now we've looked at double replacement, single replacement, and combination and decomposition reactions. There is one more type of reaction that you should be familiar with, and that of course is the oxidation, or pardon me, the combustion reactions. So if we had a material such as the main component of gasoline. I'll give us a good example here. So we're going to call this a combustion reaction. If we have something like gasoline, which is mostly hexane, so that is C carbon C6 H14, that's a liquid. It's formula typically for hexane, the main component, a main component of gasoline. And if we add oxygen to this mix and throw in a little starting spark, we're always going to get, in this case, carbon dioxide gas plus water. It's assuming everything works perfectly, of course. So in this combustion reactions, we're always looking at the formation of CO2 and H2O. So of course, this is not balanced, so we need to look at it in the balanced form. And if you recall what we did earlier, is say, well, let's put a 1 here, and now we say C6H14 is a 1 plus O2 yields, now we have 6 CO2s, and in this case we'd have 14 hydrogens, so we need plus 7 H2Os. So now what we have is 12 oxygens over here. So we have 12 oxygens on this side, and over here we have 7 oxygens. So together we have 19 oxygens on this side. So we have to end up with 19 oxygens on the other side. So the easiest way to do that, if you recall, is to make the 19 the numerator, and the 2 becomes the denominator, and now it's mathematically correct, but we need to fix it so that it is chemically correct also. So we have to multiply everything through by 2. So we say 2 C6H14, by the way, that's a liquid, plus 19, because 19 over 2 times 2 is 19 oxygens, yield a total of 6 CO2s, it's a gas, plus 7 H2O as a liquid. And this is typical of combustion reactions. In further details here, you'll see, if we were to break this down further, that it is also an oxidation reduction reaction. And of course, the oxygen is the oxidizing agent, the hexane is the reducing agent, and in general, all fuels that we typically employ are reducing agents if they're going to be burning in an atmosphere of oxygen. And here we have the production of CO2 and H2O in this example of a combustion reaction. What we need to do is to make sure that, number one, the combustion reaction is written out initially as to what we know are the starting materials, the reactants, and what we know are the products. Then we also have to make sure that it is appropriately balanced so that we have the same number of atoms of each type on both sides.